Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru, so I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. Our topic today is vehicle network communication overview and diagnosis. Now, I know that vehicle network communication systems are a pretty hot topic, just evidenced by how many views we get on YouTube just for those videos that we've done in the past for these. So this is going to be a good overview and diagnosis kind of combined into one. We'll talk about a few different network types and how they're laid out and how they work. And then we'll just get into some more actual diagnosis as we go. So let's start at the beginning. A network. Let's define what a network is. So a network is a system that utilizes information through all available resources. So any modules or nodes that are connected to each other can use information from each other. For example, if a transmission control module needed a wheel speed sensor input from the ABS control module, they can get that information over the network. Now, there's a few types of networks that you may already know and be aware of that you probably use day in and day out. First one is LAN. So that's a local area network. So that'd be kind of like your network in your shop, your Wi-Fi, as it were. And then there's WAN, which is wide area network. So that's multiple LANs connected to each other. And that's just a really fancy way, I guess, of describing the internet, just a wide area network. Now, the types of networks that we deal with in the automotive industry, we're going to talk about CAN, which just stands for Controller Area Network, not Car Area Network, like some folks might think, but it's actually Controller Area Network. It's used in more than automobiles, it's used in factories and so on as well. Then we have LIN, Local Interconnect Network. That's a kind of a single wire bus, point to point. And then DOIP, which is kind of a fairly newer protocol. That's Diagnostics over IP. That's Ethernet that you might be seeing out there in some vehicles as well. Now, what a network does is it works on what we call a voltage differential. What is the difference in voltage between the high side and the low side of the signal? And it's going to vary depending on what the specifications are for that type of network. So in this example, we're looking at a LIN bus, which we'll talk about in a little bit. But what LIN works on is about a 12-volt differential. Now, you see it does not go down to zero, and it's over 12 volts here at the top, but the difference between the top and the bottom is about 12 volts. They usually give you a little bit of room either side of that, just to give you just kind of as a buffer, right? So it's about 12 volts. So it's not necessarily going to be 12 volts to zero. It could be anywhere in that range. This one happens to be off an alternator, so it's actually has to be running. So you're going to see alternator voltage about 14-ish volts. 13.35 in this case, down to 0.91, which gives us a 12-volt differential there. So different types of communication networks that you'll find on cars, and we'll talk about a fair number of these today. Low-speed networks, it's going to be kind of your earlier networks. J1850, we have both variable pulse width and pulse width modulated type signals. We'll take a look at what those look like. We also have K-line, which is pretty common on Japanese cars, Asian vehicles. LIN bus, which is going to be used fairly commonly on many cars nowadays. CAN bus, of course, that's pretty much the standard. Then we have CAN FD, which is a faster version of CAN. We'll talk about that because that seems to be coming up a lot in conversation lately. FlexRay, MOST, which is a media transport. It's used a lot for audio and video in the vehicle. And then Ethernet, which is that diagnostics over IP, which some vehicles use now. And some vehicles also use it internally as well. Really, it's going to start at the diagnostic link connector. So your data link connector. So this is since 1996, this has been standardized across pretty much the world. So pin 1 can be used for low speed CAN communications. I've seen that on GM especially. Pin 2 is going to be your J1850 variable pulse width. That would be a single wire network. Once again, often used by GM. And then we have J1850 pulse width modulated positive, which matches with the pin 10 negative. So those are standardized pins. That's where they would be. Sometimes now on modern vehicles, when we're not using those lower speed networks, we also may find CAN bus on some of these other pins too, but we'll get into that in a minute. So J1850 variable pulse width is single wire, and J1850 pulse width modulated is 2-wire. That was often used by Ford back in the day. Pin 4 and 5 are ground, so one's for scan tool, one's for common signal. Pin 6 and 14, that's going to be your main CAN bus. So CAN bus can be on other pins. You're going to have to look at the wiring diagrams, and we'll talk more about that as we go. But your main network with your engine, transmission, body control, that's all going to be on pin 6 and 14. Pin 7 is going to be your keyword or K line. And then keyword L line, sometimes that shows up if they do a 2-wire on that one as well, pin 7 and 15. Pin 16 is always power. So really, if you know you have power and you know you have ground, that's a good place to start. If you do not have power here, that's probably where you're going to want to start, because a lot of that is usually linked to the ECM, the very same fuse, or provides power from the ECM in that case. So let's talk about single wire networks real quick. We talked about J1850. So the J1850 variable pulse width bus consists of a single wire with a transmission rate of about 10 kilobits per second. So this one's kind of the slowest of them all. J1850 variable pulse width uses a 7-volt differential. So you'll see 7 volts difference between the top and the bottom. J1850 pulse width modulated bus is a 2-wire bus with a transmission rate of 41 kilobits per second. And that uses a 5-volt differential. So if you were to look at it on the screen, you would see a 5-volt difference. So here's the case of the variable pulse width. You can see it goes up to about 7 volts at the top, 0 volts at the bottom in this case, and that would be on pin 2. J1850 pulse width modulated, we can see we got about 5-ish volts right there, 4.3, 4.5 on this particular vehicle. And you'll see when one channel goes high, the other one goes low at the same time. They kind of mirror each other. So that's your ones and zeros, your bits and bytes going back and forth on the on the different legs of that, right? So we can see how it kind of goes up and down. Then there's K-line. So K-line consists of a single wire with a transmission rate of around 10 kilobits per second as well. So that's going to be very similar to your J1850. And then in this case, it uses a 10-volt differential. So here's a K-line here. And this is off of actually off of my Subaru. So Subaru is kind of weird, not to go off on a tangent about Subaru, but they have both CAN bus and K-line for their diagnostics. It just kind of depends on the age of the vehicle. My vehicle happens to have both. So it has a K-line for diagnostics, and it has CAN bus because it has to have CAN bus because that's a standard too. So in this case, we were able to pull the K-line right off, and you can see it's a 10-volt differential, square waves. When you see an up, that's a 1, and when you see it down, that's a 0. So ones and zeros, on and off, that's your data. Then we have LIN bus. So LIN was specially developed to achieve cost-effective communication for intelligent sensors and actuators in motor vehicles. So it is a master and a slave, or it could be multiple slaves. They can just be kind of daisy chained together. So it's going to send digital data. It's not really an on-off. It's going to send digital data back and forth between, say, a window switch and a window motor. It's not going to tell it to turn on. It's going to tell the module to turn it on. So it's just sending data back and forth. It's used wherever we don't need the bandwidth and versatility of CAN. We don't need to send a lot of information. It's really just more of an on-off, up-down type thing. It's consists of a single wire with a transmission rate of up to 20 kilobits per second, and it uses a 12-volt differential like we saw earlier in the presentation. So some examples of where you'd see that is roof. So light sensors, light controls, sunroof, steering wheel controls for sure, seat controls, engine, little small motors, grill shutters, climate control, doors, mirrors, central ECUs, mirror switch, windows lift, seat controls, etc. So it's all those little switches and motors. It's pretty much what it boils down to. They use LIN. And there's the example of the LIN signal again, about a 12-volt differential. You can see all the ones and zeros going back and forth in those little data packets. So that's the gist of these data networks, is that they're going to send bits and bytes, ones and zeros back and forth. That's all a computer really knows is on or off, binary, 1 or 0. So it sends ones and zeros in a certain combination, and the computer can decode that and figure out what that actually means. And then we get to CAN. So CAN is pretty much your standard nowadays. It's been standardized since about 2008. High-speed CAN consists of 2 twisted wires with a transmission rate of 100 to 500 kilobits per second. That's standard CAN. There is some higher speed CAN that can get up to 1,000 kilobits or 1 megabit. One signal circuit is identified as CAN high, and the other signal circuit is identified as CAN low. At each end of the data bus is a 120 ohm termination resistor between the CAN high and CAN low circuits, and that kind of is your stopping point at the end of the bus. So this is an oversimplified drawing of a CAN bus, but as you can see, we got termination resistors on both sides. Oftentimes, that resistor can reside inside a control module. Now, if you want to test a network, you want to ohm it. If you want to ohm it out, because there's not a lot you can do with a meter, you really need to use a scope, and we'll get into that in a minute. But if you wanted to use a meter and you wanted to ohm out the lines, then you could you would plug in at 6 and 14 on the DLC. You want to make sure the power is off to the vehicle, otherwise that can skew your number. And you should see 60 ohms, because 120 ohms and a multimeter is going to take the average between the 2 lines that it's reading. So 120 ohms on each. Divide that by 2, you get 60 ohms. So it should be about 60 ohms when everything's working. If you get 120 ohms, you got a problem. It's going to be kind of an open or a short. So nice thing about CAN bus, though, is it's a modular network. I can add modules to the network, and they will start communicating, as long as they're programmed properly. I can add a few more modules if I want to. There is a limit. Not 100% sure how I would quantify the limit. But once you get too many modules on the same network, you're going to have data collisions. You're going to have a lot of what's the word I'm looking for? Like a traffic jam, right? You'll have a traffic jam of data, and things might not necessarily be able to go where they need to go in the time that they need to get there. So what some manufacturers have done is they've actually split out multiple CAN buses on a vehicle. And we'll see that a little bit later when we look at some wiring diagrams. But by and large, you can add modules up until that, whatever that point is. Even take a few away. You can take all the modules away. You can have just one module on this CAN bus connected to the data link connector, and it'll still communicate and it'll still transmit data, even though it doesn't need to share it with anything else. You'll still be able to communicate with it. And if I was going to look at a CAN bus pattern on a vehicle, this is kind of what it's going to look like. So ones and zeros, bits and bytes, on and off. We'll analyze this a little bit more when we get to the live portion of the program. But as I said, main bus is on pin 6 and 14 on the DLC. You could also go directly to the module as long as you knew where those CAN wires went to. Depending on the complexity of the network, you may need to actually go to the module directly. That brings us to CAN FD. So CAN FD has been a topic of conversation over the last year or so, at least in my life. So CAN FD, what that is, it stands for Controller Area Network, which is CAN. FD stands for Flexible Data Rate. So it's able to send more data with the same basic structure. So it's structurally identical to traditional CAN. You're going to have twisted pair wires. You're going to have 120 ohm termination resistors. But due to the way the data is structured, it can carry more data and it can be faster. On average, it's going to be anywhere from 3 to 8 times faster than traditional CAN. But going back to that structurally identical part, you can mix CAN FD and regular CAN modules on the same network. So that's the beauty of the CAN FD. So it just allows the manufacturers to send more data at a faster rate while still using the base CAN structure that they're used to. We don't need to get too deep into it, too into the weeds here, but if we look at the top part, that is what a CAN bus data frame would look like. Right, so we can see the start and the end, the data field, data length code, all of that stuff. And this is like, electronics engineers, programmers type thing would be worried more about this. But the big change is kind of in the middle here, where they're going to change it's going to allow them to change the rate of the bits and so on. It also allows for better error correction. So we can see a lot of it's the same up until it gets to this middle part, and then the end part's going to be the same too. So if you were to look at this with a scope, if you're used to looking at a regular CAN bus, it's going to look pretty much the same. It just might be a little bit more, it might be a little longer in length, but it's going, and it might be a little bit faster. So the frequency might be a little bit closer together. But essentially, they communicate in the same way. So you really don't need to change a whole lot when it comes to those vehicles, and even when it comes to scan tools. So I know that some other scan tool manufacturers that are not Snap-on have these CAN FD adapters that you can buy, wherever, Amazon or whatever. And they say they're for 2018 and up GM and Ford vehicles. Well, what they don't tell you is it's not for the North American market, at least right now. And as far as I know, it's not in Europe either. So since the other manufacturers make global tools, that the same tool will work pretty much anywhere in the world. So in certain countries, you may need that adapter. So I know in Latin America, South America, pretty much Mexico down south, there are some vehicles that use CAN FD that go to communicate directly to the scan tool. Otherwise, like in North America above Mexico and the UK, there are no vehicles that use CAN FD to communicate with the scan tool directly, like a direct interface where you would need that. However, I know this has a global audience. So if you are in one of those countries that has these cars, for example, this is a Chevy Onyx right here, that's only available down in Latin America, Brazil, what have you. And you would need the software, of course, to communicate with that vehicle anyways. But in those cases, depending on the tool, you may need an adapter, and the adapter would be available. But since there's none of these vehicles up here in North America, we don't sell it in North America, but it would be available to any of these other folks. So if you have an Apollo D9, a Triton D10, Solus Plus, or the S9 scan module that came with the Zeus Plus, or the second iteration of the Zeus, the black one, you don't need an adapter. It's included in the software. It's built into the chip, so you don't have to worry about it. Anything else, like either the D8s, Solus Legend, Solus Edge, Modus Edge, any of those needs an adapter cable, and it's just a simple. It looks just like if you've ever seen the Ethernet cable, where it's got the big pill in the middle. The adapter cable would be required for that. It's just it'd be a separate part number. It's not the same as the Ethernet cable. It's a separate cable, and it would tell you what cable you would need on the tool. I know I got a message from a franchisee that was in South Texas a couple months ago, and they said, hey, a customer is plugging in with the tool, and it says it needs this adapter. And I said, well, we don't have the adapter available in North America. And I said, what kind of car is it? And he said, well, it's a Chevy Onyx. I said, okay, well, they don't make those up here, so it must have came up from Mexico or what have you, and really nothing we can do, because you would need the specific scan tool software for that vehicle anyways, which is not also in the US Canada market. So not sure how they fared after that, but just be aware that they are around, but they're not necessarily supported on North American software, US and Canada software. I do know Mexico's in North America. Here's just an example of what you would find in a US vehicle. So this is a 2023 Mustang Mach-E, and that uses CAN FD. But it uses CAN FD inside the car, not communicating with the scan tool. So we see on the scan tool here, we have two channels of CAN, the pins 6 and 14 and 3 and 11. Like I said, some manufacturers use multiple CAN buses to the diagnostic connector, but there's the diagnostic connector there. Then you can see it goes into the gateway module. And we see we have Diag 1 CAN and Diag 2 CAN. Those are two channels of CAN. And then we have mid-speed CAN. We have some high-speed CANs internally, and then we have high-speed CAN FD right there. So those go to a few modules. We'll take a look at this wiring diagram in a little bit when we go live. But you can see it's high-speed CAN inside. There's other vehicles. They use Ethernet internally. They don't communicate with the scan tool with it. Not sure why they haven't made that change. It's probably for their own factory scan tools to not have to worry about updating them, I would suppose. But they are out there in certain places in the world, just so you're aware. As of right now, as of fall of 2023, you really don't need to worry about it too much in US, Canada, UK. All right, and then there's FlexRay. So FlexRay has actually been around for quite some time as well, mainly used in European cars. But the FlexRay bus consists of two twisted wires with a transmission rate of up to 10 megabits per second. So that is the fastest by far out of any of the networks we talked about today. And I think because of that, because of the speed, it only has a 1 volt differential. So it's turning on and off ones and zeros very, very fast. Very similar to CAN. Has a signal high and a signal low is what they call it. And then at the end of each data bus, there's an 80 to 100 ohm termination resistor, depends on what the manufacturer put in there. So there's a little bit of leeway in the spec as to what they can use for a resistor. And you can see it's kind of like CAN, but it's very, very small when it comes to the ups and downs of those data packets, right? So we're getting progressively smaller, and it's more because of the speed, and that's why it's a much smaller pattern. So now let's talk gateway modules, because I already kind of mentioned it earlier on that Mach-E, right? But for data to be sent between different networks on a vehicle, like high-speed, low-speed CAN, mid-speed CAN, CAN FD, whatever networks on a vehicle, you need to use a gateway module. There also may be multiple gateway modules on a vehicle. You would want to refer to whatever manufacturer's wiring diagram. Another way to think about it is these modules are the router on the vehicle's network. So they're going to route the signals where they might need to go. So this is an example on I think it was an Impala. So we see all these in the red box are on the high-speed network. The green boxes are on the low-speed network. And then the body control module in this case is the translator between those. We've got the diagnostic connector here. We see all the diag wires go in here, and then it sends the signal to wherever it needs to go, either the high-speed or the low-speed bus. Speaking of speed and bus, so GM has announced a little while ago, and announced in 2019, actually, so that's like 4 years ago now, GM's digital vehicle platform. So this is their new platform that they've been using the last few years. It debuted in the 2020 Cadillac CT5, and it's pretty much in most GM vehicles at this point. The capability of this system is capable of processing 4.5 terabytes of data per hour, and that is a five times increase over what they were using before. Uses Ethernet internally inside the vehicle up to 10 gigabits per second, and it also offers over-the-air updates to the car. So you may not be flashing vehicles nearly as much anymore, at least on these GM vehicles. So let's talk about testing networks using your scope, because if you're going to test a network, test for the integrity, look at the signal, you really need to use a scope to do this. So you need to have a high sampling rate lab scope. So use the lab scope feature in your Snap-on scan tool if you have it. Access the pins at the DLC connector for the network you're working on. I recommend using a breakout box to lessen pin damage. You don't want to front probe it, and you don't want to back probe it. Set the voltage scale to 10 volts to start, and then set the sweep time at 100 microseconds. You may need to adjust depending on what the signal looks like, but that's pretty much where it's a good place to start. And there's an example of one of the breakout boxes we have. We also have some that are more fancy with voltage readings and lights and stuff. This is the basic one, the YA11167. And like you see here, we're just, in this case, we're at power and ground, but you would see 6 and 14. You can just plug in right there for your CAN bus or whatever other bus you need to access on the vehicle. And it's going to look something like this. When you're looking at CAN bus, you'll just see some signals going by in between the high and the lows. So it's going to look kind of like that. If you want to put your trigger in there, it's going to move a lot less. But what we're concerned with is the high range and the low range. So the voltage reading should be between 2.5 to 3.75 volts on CAN high. And then 2.5 volts is going to be your idle state. And then anything 2.5 volts down to 1.25 volts is going to be your low side. So Idle speed is going to be in the middle, so that's your ones. And then your zeros are going to be your pulses back and forth. And then when it stops communicating, it's going to go back. So like I said, we're only interested in the top and the bottom. So anything over 2.5 to 3.75. So it's going to be from here to here. Anything over that's going to be bad. Anything under this is going to be bad as well. So really your range is going to be 3.75 to about 1.25 volts, give or take. Now, if I have a lot of noise, if I have corrupted data inside, it's going to drop off the packets. Even though there's electromagnetic interference disturbing these packets, the network will still communicate. It's just not going to communicate with whoever's sending that dirty data there. So if I saw a lot of noise in the signal, that's bad. It's going to cause intermittent malfunctions, and it could cause U code. If the packets are weak, if you see some big ones and then you see some that are kind of smaller and don't look quite right, it could be an internal short to ground on the controller. If that happens, the controller's packets are going to drop off and they're going to stop asking it for information, cause intermittent function in U codes. So on the high side, if we have a short to power, it's going to be up maybe about 5 volts. If it's normal, like we said, the top will be 3.75 volts. If it's shorted to ground, that'll be down around 0 volts. If it's out of range, it's going to be controller issue. Same thing with the low side. It can be shorted to ground. It can be normal. It can be short to power. And then we could also have both do the same thing. So both could be shorted to ground. Both could be normal. Both could be shorted to power. And then we could have just one side short to ground or one side short to power would happen as well. It just kind of depends on where the short is in the line. So for example, low errors, short to ground, could be an internal short to power or ground. Abnormal control, these are all over the place, not really mirrored at all. So they're kind of up and down and all around. It's going to drop whatever requests. So sometimes if it decides to stop communicating, you may not be able to see them all the time, but when it's sending erroneous data, you'll be able to see. If it shorts the ground one side, you can see we got the high side shorted to ground. It's still going to communicate, but at a lower frequency. Same thing with the low side. If the low side does, it switches to a lower frequency. And then if both sides are shorted to ground, it's usually no communication at all. Most likely a result of physical damage, like the wires have been cut, or maybe you got an accident, it got pinched and severed there. So if you have no communication at all, that's a good place to start. So let's look at a case study about a bus problem. So we had this 05 Chevy Silverado, and it had an intermittent hard shifting problem, and it was like very, very intermittent. It will intermittently shift hard, and then when it's happening like that, it'll also act like it's constantly in third gear from a stop. Like it takes a long time to get off the line, right? Comes and goes at random. Doesn't depend on weather conditions, time of operation, or anything. It can be hot, can be cold, can be snowy, can be wet, can be dry, can be driving for an hour. It happened to be on this day. It didn't do anything until he got to me, which was nice. So he was kind of driving. We were meeting up in a parking lot, and drove an hour and nothing happened. And then as soon as he pulled in the parking lot, it started messing up. So that was kind of nice that it happened right then. But we hooked up our scan tool and checked for codes. So there's the vehicle there. It's a 6.6 turbo. We went and did the code scan, and we ended up with 2 pages of codes. Most of the codes in there were U codes. So U codes are network communication codes. And then if we look down here, we got a 101, lost communication with transmission, lost PCM, class 2 data circuit malfunction right here. So that's where we're going to start with that U1000. I'm going to take a look. We're going to go to OEM testing and see what it says. It says module connected to the class 2 serial data circuit monitor for serial data communications during normal vehicle operation. Operating information and commands are exchanged among the modules. When a module receives a message for a critical operating parameter, the module records the ID number of the module which sent the message for state of health monitor. So if it doesn't find that, and it's not able to find that module, then you're going to get a code. So conditions for setting this code is a node alive message. So in other words, the module has not communicated that it's working. If it hasn't been received from an unidentified module in the last 5 seconds after establishing communication, then it will just say, hey, we have a problem. When that happens, the module is going to use a default value for whatever missing parameters that were needed. So this is where you might get, if you're looking at scan tool data, it's just going to use a substitute data value. And then that could be a problem as well when you're going to diagnose it if you didn't realize that this is the problem. So we're going to hook up a scan tool and we're going to see if there are any codes in this range here with history data. Yes, we did. So we're going to go to the DTC list. And then the first one we came up with, the lowest number was 101. So we're going to go in there. And it says different problems that could happen. Voltage applied to the modules is normal. Engine needs to be running. And that's going to give them a message that hasn't been received. All right. So we do the diagnostic system check, which would be scanning the vehicle. We went to install scan tool, retrieve DTCs. Is 0073 set as current? No, it is not. So we go to step 3. It says turn the ignition on, the engine off, and the following circuits and module not communicating on the bus for open or short or ground. So we're going to check battery positive, inputs and outputs, ignition voltage inputs and outputs, and so on. Or instead of going through all that and testing all those different things, why don't we just look at the bus and see what's going on? Now, in this case, it's a single wire bus on the vehicle, and here's what it looked like when it was communicating. And we can see that doesn't quite look right, does it? Doesn't quite look right. It's supposed to look like a square, but instead it looked like this. So what this indicates, and this can be useful for many different signals. If it's a signal that pulls down to ground, if it looks like this, where it kind of curves when it's pulling down to ground, that means that it's taking a very long time to get to ground, because what is a scope if it's a value over time, right? So this one actually made it to ground. This one never made it at all because it was too short of a pause between here. So it's coming down and it's just not making it to ground, So that is a problem on the ground side. It's not able to pull it down fast enough to pull it down to ground. So that is an issue. Like I said, it's a 7-volt differential though. So there's your 7 volts at the top, 0 volts at the bottom. In this case, it makes it down to 0.69 volts, which is not far enough to, that's enough to cause an issue. So we went and it says go in and try and find and disconnect, inspect the harness connectors, disconnect things, try and find the module that's not communicating. What we did instead is we had this tool that unfortunately they don't make anymore, but it was a data bus fault finder. And what it does is it checks the bus for power. It shorts the power, shorts the ground. So there we see in the middle, it says short to ground. And then we have 3 modules that also say shorted to ground, look kind of like this. So the green lights on the bottom means the module is connected to the network. And then we see we have a bus short to ground. We have 1, 2, 3 modules that says short to ground. So in this case, we have the TCM, the PCM, and the BCM are those 3 modules right there. So D, F, and H. So the problem lies in one of those 3. Now, the nice thing is we can use the buttons that are on this to take that module off the bus and then check it with the scope. So we have the scope hooked up and we went through one by one, turn them on, turn them off. When we finally got to the transmission control module, it looked like this, looked the way it was supposed to. So we knew at that point that the transmission control module was the one with the problem. It was the one screwing up the bus. Kind of made sense with the shifting problem, but you never know. Could have been the PCM as well. So when the TCM, as I said, was taken offline, a good pattern showed up. New TCM was ordered, installed, and set up. And then we check back to the information to verify the repair again. And it says make sure there's no DTCs after it was cleared, after we road tested it, drove it, nothing left, no codes, and that is case closed. So let's go live and look at some wiring diagrams and some other things that we can do with the tool. All right, so here's our tool. So let's look through. First things first, if I'm going to investigate, if I think I have a network issue on a vehicle, I really need to check a wiring diagram to understand how that network is laid out and how I'm going to access it. So let's pull up a couple vehicles. We'll start with something super simple like an 05 Jeep Wrangler. All right, so if I go into my repair information, I'm going to pull up our wiring diagrams. And if we just go to our wiring diagrams in general, we can go into the system wiring diagrams, and then it's going to be under, if you're using Schottky or Mitchell, it's going to be under computer data line. So it's going to have a separate data line circuit. So if I open that up, we can see here's the DLC here, and this is the entire network on this 05 Jeep. Right, so I have 1, 2, 3, 4, 5, 6, 7 different modules on there. Let's see, we got ground, power, And then we have some individual wires on their own proprietary network here at SCI. And then we also have the PCI bus here. So it's going to plug into the computer. It's going to go into each of these modules down here as well. And then if we needed to get into, say, the ABS controller is going to be on a different line. It looks like it's on a K line. And then, yeah, same with this one as well. So this one does have its own proprietary network for like the scan tool. But we can see it's a fairly simple network. It should be, if we do have a network problem, it's going to be a single wire, not all that complicated. Let's change to Subaru. So we talked about the Subaru, how it has two different lines as well, just kind of like that one, but in this case it has CAN and a single wire for the scan tool. So we pull up our computer data lines. Once again, it's on a single page. It's got more modules, but it's on a single page. So if we zoom in a little bit and we see the DLC, so we know we got power, 4 and 5 are ground, right? Nothing over here. Then we have 6 and 14, right? So we got 6 and 14, which is going to be your CAN bus. So if I zoom out a little bit, we can see the CAN bus kind of goes to the ECM, and then the VDC module, which is vehicle dynamics control, and then it actually spreads out across all these other modules as well. It just doesn't go through these splices for some reason, the highlights, but it goes through all these modules here. There's a splice point right here as well, which would be good to know. So if there is a joint connector, in this case, this is on the left-hand side, right above the fuse box. And the little joint connectors in here look kind of like fuses. So one big thing they did tell us at the training school is, hey, don't mess around with these, because if you unplug something, you might lose communication, because it really hooks up to the rest of the vehicle in that case. So all the vehicle communication comes through here. So if you lose communication with the meter, the AC control, the audio, then it's got to go through here. So if that's the point where it stops, you see, just by reading this wiring diagram, you see it starts at the DLC and it goes through here. So if I were to have communication with the body control module and all this stuff, but I don't have communication past this block, then I know there's a problem somewhere in the block. And actually the block gives me a test point as well, if I know exactly where it's going to go. So that's kind of nice. If I reset this, though, we'll see we also have, gotta reload this diagram here. So we see we also have this block right here. Now this block comes from the DLC, and that is a single wire. That is a K line, and it goes into this block. It's a distribution block. So once again, it gives us a junction point where we can test communication of different modules. And you see in this case, this is the old style single wire point-to-point to modules to get to the body control module. And then in that case, from the body control module, if I need to communicate with anything else, that's going to be over CAN. So it's going to depend on what module needs to communicate as to whether or not it goes over CAN or if it goes over that K line. So we can see it's just the main modules, right? So ECM, TPMS, impact sensor, vehicle dynamics control, transmission, body, and then up here is the airbag. So all the major modules on the vehicle can be accessed through that one line, and then everything else is on the CAN bus. So you got to kind of get used to reading through wiring diagrams in order to get here. All right, let's go to 2 more examples on the diagram. So we got the Mustang Mach-E that we looked at earlier. So that's the electric Mustang. And that is going to have, like I said, it's going to have CAN FD in it. So in this case, we have 5 pages, so it's getting more complex. This is 2023, as I said. So it's going to be CAN from there to the gateway module. Then from the gateway module, we have Ethernet, 1, 2, 3, 4 different Ethernet networks. And then we also have our CAN FDs. So it's going to be this right here. It's going to be our CAN FDs. So the CAN FD in this case, internally in the vehicle only. Image processing modules, that's going to be for your camera, your front view camera, Secondary onboard diagnostic control module. It's going to go across over here as well. It's going to go in vehicle dynamics control, powertrain control module, evac and fill module, power steering control module, driver status monitor camera. Oh, by the way, that's a thing too, where it takes a picture of your face to make sure you're paying attention. And analog brakes are all on the all on the can. And now the can FD, not really as a rule, but just kind of industry wide, is what they've kind of adopted. Is it's usually going to be on like your major stuff like your ADAS, electric vehicle control modules, that sort of thing. So that's why I picked an electric vehicle, because I figured they're probably going to have it. In this case, it definitely does. And then one more before we get into actually testing. We'll do this Silverado. So this one is the most complex out of all of these. And I'm sure there's other ones out there that'll be pretty complicated too if you just pull them up. But we only have so much time. So pull up my system wiring diagrams, pull up my computer data lines, and you say there's 13 diagrams, 13 pages of diagram here. And then if we look at the DLC, that DLC is full. Every single wire on this diagnostic link connector is used for something. So there are multiple CAN buses on this field. Multiple CAN buses. Let's see, what's pin 2 and pin 10, I think would be. So yeah, private serial CAN bus. So that is that they're using where the J1850 bus used to be on the pins 2 and 10 in order to do a separate CAN bus. So we can see all these modules. Low reference, Ethernet bus, auto SAR CAN bus, which I think is their diag bus, private serial CAN, Ethernet bus again. So lots and lots of different buses coming through this serial data gateway module, which is on the vehicle, and then it disperses throughout the rest of the vehicle. So you can see how it kind of goes out. It takes all of these disparate wires coming in, and then really it just goes out to these main couple wires here. Really, I mean, there's a couple different modules that are on separate wires, but by and large, it's going to be through these couple wires here on the AutoSAR. So this is that new Global B, the digital vehicle platform they were talking about, that I had that one slide on, can process 4.5 terabytes of data a second or a minute, whatever it was. But yeah, it's gonna go run across here. I'm sure it's gonna run across all 13 pages, and it's gonna go to the other end wherever that is, I guess. But it's going to end up with the telematics control module, and then it goes out from there. So we have CAN bus 5, CAN bus 6, Ethernet bus 6. So within these vehicles, they're very complex. It's just a whole mess of wires everywhere. Ethernet, CAN bus, multiple buses. As I said, once CAN bus gets too many modules on it, you get data collisions and backups. So that's why they started going out into multiple buses. They also went into Ethernet, CAN FD, all these faster technologies inside the vehicle, not communicating with the scan tool. So sometimes if it's a really complicated network problem, you may have to get in there into the module itself, past the gateway module, in order to diagnose. All right, now let's talk about actually diagnosing the problem, right? So I could go into my scope, just straight into the scope, pull up my lab scope, and then see what I can see. So in this case, it's not quite set up right. It's set to 10 volts, but it's at 200 milliseconds. And I only have one channel. In this case, I'm testing a CAN bus. So I need to turn on channel 2, make sure that's set to voltage as well. 10 volts. Once again, that 200 milliseconds is way too long for a CAN bus, because the CAN bus is very high speed. So I usually say start at 10 volts and 100. So there's 10 volts and 100. We can actually see what's going on. Maybe I pull out a little bit further, go to 200. There we go. Now I get a whole pattern. This is a complete block of data, CAN bus data, on this simulator there. So we can see the ones and zeros, the bits and bytes. If we wanted to analyze this, we kind of set it up like this and see what we got for voltages. So it should be about 2.5 volts right here. Looks like the battery's getting a little low on this thing, so it's about 2.36 volts. And then when it transmits, like I said, the high side goes high by about a volt, volt and a quarter. Low side goes low by about a volt, volt and a quarter. And we can see it's about a volt on either side. So it's 236 to 327, and then 237 down to 138. It's about 9.9 and 0.99 on the two channels. So they should be pretty even. flat tops, flat bottoms, no noise, no shorts to ground, no shorts to power. So in this case, it looks like everything's good. Now that's a manual setup if I wanted to do that. And I did that pretty quick because I know where I needed to go to understand that. But if you want to learn more about CAN, we can go into guided component test if you have the tool of the scope. And if we go into classes, under how to here, there should be a CAN bus class in here. It's the first 20-minute class. Let's see, 20-minute CAN bus class right here. So we can talk about basics and fundamentals, bus arbitration, CAN voltages. So we can talk about the different voltage ranges they need to be in, CAN low, CAN high, signal quality, different waveforms. Oh, I hit back too far. CAN bus there. Waveforms. All right, so we can see the different waveforms. Here's good. Here's one with an open. Here's high side with an open. Here's low side, short to positive, both short to positive, and so on and so forth. So you can see what the different modules look like. Here's one that, depending on where the short circuit is taking place in the test point, it may look like this. So it gives you a lot of really good information as to what known good and known bad should look like. Also, if you wanted a general setup for CAN bus, you can go into power user tests. You can do a dual channel test, and there's a CAN bus test in there. All I got to do is hit view meter, and it's going to set it up. Look at that, and it's going to show us what it's supposed to look like too, which it does. Now, I will tell you this extra little bit at the end is not on every manufacturer, depending on how they wanted it set up. So in this case, they call this an ACK bit or an acknowledgement bit. So this is the end of the transmission. So I call it like the period at the end of the sentence. So we're going to tell you all the data you need, and then here's the end. I'm done. So that's what that is. You may not see that depending on the manufacturer. In this case, I'm hooked up to a BMW. So BMW does that. So that's what it looks like, but it may not in all circumstances have that at the end. So don't worry about it if it does. If you see some spikes in the middle, that's a different story. And it'd probably be up in like the 5-volt range. So that might be something to worry about. And then you want to look at the tops, make sure they're not all like skewed or messy. And then the last way we can look it up, other than doing it manually or doing it that way, is we can pull up the vehicle. And the majority of vehicles in the tool that have CAN bus, if you go into engine, you're going to see a test for CAN bus right there. And then there'll be a signature test. And it's going to tell you where to plug it in on the vehicle. In this case, they want to plug it in the ECM. Hit view meter. It's going to hook up and it's going to display. I know it's a lot of information to go over. There are other videos that we've done in the past that cover some of this information a little bit more in depth as well. We just wanted to get some more information out there, especially on like that CAN FD and some of the newer vehicles that are out there and how complex that they have become. So that is network overview and diagnosis. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully, we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week. Have a good night and take care.